But today I'm going to talk about data science. So the provocative question is data analytics going to replace science? And just a little bit of background of myself. I'm professor at ETH Zurich, and actually I was one of the early adopters or promoters of data science, and actually they like using pictures that we have produced in my team. But today we'll focus really on this question: will we see the end of theory or even the end of science as we face the data deluge? That means really a huge, overwhelming mass of data. And I'm skeptical about it. I should be honest about it. And that's why we need data science and not data analytics. And my skepticism started early on when I met Jeremy Howard on his roof terrace. We were talking about big data. And he said, you know, one of the surprising discoveries that we made was that orange stars break down less often. For a physicist like me, it didn't make sense. And in fact, other people have recognized that as well. And so we need to be more critical. But let me give a little history of the digital revolution. So as you may know, it all started with ARPANET, developed by the military, the precursor of the internet. That was in 1981, and then in 1989, the World Wide Web was invented. Virtual reality came in 1993, and then all those internet trading platforms. That means we had a new kind of business or economy grown in this virtual world. Social media came up around 2003-4, Twitter 2006. The Internet of Things also in parallel came up. So we expect to have multiple times of the number of human beings on this earth in terms of sensors. And it goes so far that in 2017, they had invented new medical pills that would basically send data from within the body to your doctor or whomever. So there are many reasons to collect data. First of all, to make money, so data is the new oil. Second, for power, because knowledge is power, as people say. Then for security reasons, to improve the state of the world, to make it more sustainable, and to save and improve lives. And actually, probably a lot more reasons, and so people are collecting a hell lot of data. You all know this. Just to remind you, in case you're not so much interested in it, but I think we should all be aware of it. It goes from our shopping habits and consumption patterns over our mobility patterns, our social contacts, our files, our emails, the texts that we read, the questions that we have, the things that we say, the movies that we watch, and also in the meantime, smart TV is basically watching us in the living room or wherever. Smart glasses haven't made it yet into the mass market, but that may change. And then there are game consoles. There are these cleaning robots. There are smoke detectors, some of them including cameras apparently. There are trackers that track your behavior online. And besides that, there are a lot of security gaps of hardware, of software. Then modern cars are spying on us, and our smartphones basically too. Of course, we're used to the circumstance that you would be indicated what sensors are being activated if the camera is on, for example, or the microphone is on. But you can turn the gyroscope into a microphone or the accelerometer into a microphone, it will not be indicated. So basically, yes, it's possible to listen to what you're saying all the time. And the NSA has tools to find your voice. I mean, even if you left your phone at home and talk to somebody else at the pool bar, and that other person has a smartphone with her or him, then the NSA will be able to identify you, to locate you, to figure out what you're saying, whom you're talking to, and translate it in real time and mine it for certain kind of keywords. And they can also identify your emotions, whether you had a glass of wine too much last night, whether you're happy or sad or depressed, whatever. And as you all know, also spyware is being used to target activists, also politicians in office. And it also turns out that the cameras in our computers and smartphones could be opened up to spy on us. That would allow to analyze your face, your emotions, to figure out whether you lie or not. And it even goes so far that people would try to monitor heartbeats from a distance. And there have been, of course, all sorts of data deals. One of them that you may not even have recognized, of course, there was not so much reporting, was the deal between IBM Watson and Apple. And Apple basically wants to use the data that has, at least for some time, been secretly collected and analyzed for healthcare clinics, using basically just surveillance data, or mainly surveillance data. That's my hunch. And of course, what's still missing is fingerprints, but here we go. And then DNA, and I guess that's also going to be analyzed on a regular basis soon. And in fact, some politicians recognize that this could be dangerous, and that's why they have refused COVID tests in other countries. And of course, also data have been sold or shared. And now we're in 2022, but in 2020, the World Economic Forum indicated that tracking how our bodies work could change our lives, which I agree with. But they also indicated in another article, I think 2 months later, that the Internet of Bodies is already here. And I will talk about that also on, I think, Friday, my second talk. So the digital age is here. No question about it. And some people define it by the volume of storage, digital storage as compared to analog storage. Anyway, a hell of data, as I indicated, you can do a lot of nice things with it, such as the digital assistant, Siri, for example, but there are many others, as you know. It can be used for real-time language translation, for automated trading, can be used for cognitive computing and for artificial intelligence. CERN is one of the biggest entities to use big data and machine learning. And of course, advertisement is largely built on personal data these days. We move on spying on, in other words. And of course, the hope is that the positive applications would be dominating. And the question, of course, came up, can we know everything? Can we understand the human body, the brain, and even your personality? And of course, that excites a lot of people, but also there's concerns. And I'm now switching to data analytics. And I give some initial application examples. Visualization is among them, of course, and this includes the visualization of traffic congestion. The next example is, of course, search for use, scientific productiveness, scientific impact, flow of ideas, or even spreading of culture. So visualization is certainly one interesting application. Why are we doing data science, first of all? Because there are all sorts of challenges out there, such as climate change or water scarcity and international tensions, obviously, pandemics, and yeah, there's basically a need of innovative methods to master those challenges in the future or even now. Of course, the problems are here. And so besides visual representation, there are some further interesting uses of data, such as fitting and calibration of models, validation of models, statistical testing of scientific models and hypotheses, better understanding, explanation of systems, interpolation, extrapolation, prediction, forecasting, prognosis, optimization, control, or feedback, and then machine learning and the creation of digital twins. And at least the last two require big data, and the other points benefit from bigger data sets normally. And of course, then if big data is the new oil, then what is the new motor? And people say this is actually artificial intelligence or machine learning. And in fact, we have also this exponential or even faster, perhaps, increase in the power of machine learning. And we've seen some astonishing examples, such as the chess world champion was beaten by Deep Blue already back in 1996. And then in 2011, Watson won Jeopardy. And in 2015, we had Google's AlphaGo. And in 2018, AlphaFold. And it goes on and on and on, of course. All right, now we'll look a little bit in more detail into big data analytics. And the big question really is how to connect the dots. First, there are the data, but what do they mean? And in fact, it turns out that this is sometimes not as trivial as expected. In contrast to what Chris Anderson said, where basically, according to his perception, machine learning would figure out everything by itself. But it turns out that basically, if data is the new oil, then we need to learn how to refine that oil and how to distill information from data and knowledge from information and wisdom from knowledge. And it's not that easy always. So the early approach, in a sense, was what people call the Kaggle approach. So basically, a big data set was given to a number of people who participated in a competition, and they were trying to learn the patterns in the data, and then the best performing algorithm was rewarded with prize, and that algorithm was then applied to bigger or other data sets, for example, in the health sector, or to hunt down terrorists, whatever. But people participating in those competitions usually didn't know what the data set was about. So it was just a bunch of data. And we'll see that one can certainly make money, actually a lot of money with this approach, but there are some things that can go wrong. And we're scientists, right? We're interested in the truth, I hope. And so data science, machine learning are more challenging than one might think. And I'll give you about 11, 12, 13 points to highlight this. And of course, there could be a lot more, but I want you to be good data scientists. And that means you need to pay attention to a number of things. So first of all, unfortunately, perhaps no measurement is exact. And so there is always some uncertainty. And for that very reason, we cannot take those measurement data for the truth. Instead, we need to determine confidence intervals. And you can make some interesting experiments on your computer, for example, assuming a Gaussian distribution and then produce samples of data. And we'll find out that not even the average or the confidence interval will always contain the true mean value. Okay, this is a warning. And here are some more problems with data analytics. So first of all, sensitivity. And that is important, particularly if you want to do prediction. And of course, in many cases, we want to do that when it comes, for example, to the spread of diseases, to the growth of world population, to availability of oil, and when the amount of oil will go down, that can be reduced. And also climate change, temperature rise, and all of this. And it turns out that all those predictions are quite sensitive to parameter changes. So we actually don't know that well what's going to happen. And so we need to be aware of the uncertainty, and we need to somehow consider in all our policies that uncertainty, that things might be different from what we expected. There is actually an approach to measure sensitivity. It's called Thiele's inequality coefficient. I haven't seen it much in use in the big data community. There might be other approaches as well, but at least there are approaches to measure these kind of things. Then another point that you've probably heard many times, but anyway, for the sake of completeness, I'd like to make this point. Typically, you determine correlations in the data, and that doesn't mean causation. So if you find a correlation, it could mean that A causes B, or B causes A, and that could make a big difference. So, for example, whether crime causes unemployment or the other way around makes a big difference for what is the right policy. And in fact, my impression is some countries are drawing the wrong conclusions. So then those policies cannot be very effective. So how can you make the difference? There is a data science fix. Range causality is one of the approaches that's being used in order to determine possible causal relationships. But also we could have a situation where a third factor C causes A and B. And this is the case in the following somewhat ridiculous example, I must admit, but anyway, just to make the point. So the number of forest fires is strongly correlating with the number of ice cream eating children, or also people eating granita. And however, if you forbid eating ice cream or put children, at home, it will not reduce the number of forest fires, obviously. Just there is a correlation with heat. Now, as this looks ridiculous, but I have to tell you, these kind of mistakes in terms of the policies that are being applied are sometimes or even often made in reality. So it doesn't matter. we need to talk about it. And then A and B could also just appear to be correlated. And in this case, we speak of spurious correlations. And there are a lot of them, actually. The bigger the data set you have, the more spurious correlations are in those data sets, the more meaningless or even misleading patterns will you find in the data set. And here's just one example, number of serial killers as a function of chocolate consumption. If that were true, it would be very dangerous to live in Switzerland. So far, I feel reasonably safe, however. There's ways to fix this problem, actually, to bring back statistics. Something that is not so popular among some data scientists, it seems, but traditionally in medicine and many other fields, you have to formulate a null hypothesis and test it statistically in order to figure out how meaningful is a certain pattern or correlation. So there are methods for that. You need to learn something for it. It's not always a simple thing, but at least science has something to offer here. And then another point, which is kind of perhaps unexpected, is overfitting. You would think the more data you have, the better, and the more precise will be your picture of the world. But in fact, also this needs to be questioned, because this is an example of overfitting, right? You look into the skies and you believe to see patterns that are giving a certain meaning. And if you think, okay, scientists wouldn't do such a thing, then I have to tell you that, unfortunately, that's not true. There have been a lot of publications that were actually of a similar kind. So we need to learn that there's basically an optimal complexity of your fitting model. Of course, the more parameters you have, the closer you get towards representing the data set. But that does not necessarily mean you understand that data set well. I will come to more examples about it. So this danger of not seeing the forest for the trees. So if you're trying to find a certain place in a city, then it may not be useful to see every bush and every tree and every leaf, but you need to know where the plazas and the streets are. And so basically, there's a projection and simplification process to produce useful maps that are informative for people. So in a sense, less is more. It's more useful to take out some information that doesn't matter for a certain kind of application. And what may be even more surprising is adding noise to data can sometimes improve the results. And here is an example. So we've made a lab experiment, a decision experiment with people, real humans, and there was a certain kind of payoff structure or incentive structure, and people were interacting with neighbors and second neighbors. And there were two kinds of people according to the incentivation. And it turns out that one can predict the decisions of people with 96% accuracy, which is amazing. Typically, those experiments involving humans have a lot of noise. Not here, so very high accuracy, but the experimental result does not fit the simulation of that highly accurate model. So it's very different effect. And the reason for this is that small variations, some people call it noise, will trigger some instability and cascading effects that change the outcome of the system. And so the systemic outcome is very inaccurate, even though the individual prediction is very accurate. But in most cases, we're interested in the systemic outcome, not what the individual does. You're not a Secret Service person. And so what we then did is we added some noise, and you would think this will make the model worse, and that will also make the outcome worse. But it turned out that actually the macroscopic prediction, the systemic outcome, was better captured by that noisy model. All right? So there are quite a lot of unexpected things going on when you handle data, and bias is another thing. You know, in the beginning, people said, okay, people are emotional, irrational, not objective, and let's take AI systems, machine learning, basically to do a better job, because algorithms are neutral. That was the idea. And then it turns out that, unfortunately, there's bias, and some algorithms are racist in a sense. And this is partly because of the data that's being fed into the algorithms, which may already be biased. So the machine learning may learn the biases of the past and basically continue them into the future. And the danger is to keep that biased world forever. If we just leave the world to artificial intelligence. Of course, that needs to be corrected for. Also, women are being discriminated by a lot of algorithms, and a lot of minorities too. So there are some issues, quite unexpectedly so. And then there are classification problems, false positives, false negatives. And again, here you can have an overfitting and underfitting problem, but typically you will not be able to 100% accurately separate two classes of people or objects. There will be some overlap, and therefore some misclassification. And that can be quite dramatic in the implications, because we've looked into, for example, the implications of false positives and false negatives in COVID testing, and what are the implications for the assessment and prediction of the epidemic situation. And in fact, despite those tests are reasonably accurate, false positives and false negatives can give quite a wrong picture. Despite of this, there was coronavirus tracking in many countries, and in fact, some countries have used counter-terrorism tools to identify people who might have been affected. In some countries, those people were even treated like terrorists or as terrorists. But of course, in many cases, these are false positives. So people were completely healthy, but still were put into quarantine, house arrest in a sense. And it was not really justified, at least from an individual point of view. And that's why we have all these legal battles also, has the constitution be respected and so on and so on. Okay, so you can already see these kind of problems and potential mistakes can interfere with our personal life. And you will also face that if you want to have a loan, a life insurance, or some other things that require that you qualify from the point of view of some company or some government. And in many cases, you don't even know what the qualifiers are. Then validation is an important approach, which, however, I'm also not always seeing in data analytics and data science publications. So in most cases, there is a fitting to some model or some data, but that's not enough, because you can only tell the power of a model when you apply that model to another data set. So say pandemic in another country, or whatever kind of behavior in another country. And so your model may fit a particular data set that has been used to learn quite well. And the more parameters you use, the better will the fit typically be. But the prediction power of the model may go down with an increasing number of parameters if you have too many of them. So some models with less parameters can have more predictive power because you would be fitting noise. So that's kind of, again, the overfitting problem somehow. But there are validation procedures. You can learn them also in the scientific literature. Here's just an example for traffic modeling. And it's an old subject that I've been involved in for many years. You see car following data over here, measurement data. And then Peter Wagner and co-authors basically said, okay, it's about time to clear out the field of traffic models, because eventually there were 50 or 100 or 200 traffic models. Basically, every scientist had a favorite traffic model. And they say, okay, let's let the data speak and decide what is the true, the best data, the best traffic model. Okay, so they use the data to calibrate those different models, and then you see, well, sometimes this model is the best, sometimes that model is the best. So these are different detection cross-sections. But altogether, most models are doing quite similar in terms of their performance. That was kind of shocking. It was not like, clearly, this is the winner. No. Then they did validation. That means they calibrated all those models, and then they applied it to another data set to see the power. Of course, the arrow goes up as compared to the calibration step. Of course, it's a different data set, but again, there's not so much difference between the models. So it didn't really work out. If you talk about CERN, which is kind of considered to be the core of physics, understanding how the world works, elementary particles, and there should be one truth, one model that describes our world correctly, and everything else is rubbish in a sense, But the more measurements they do, the more theories pop up that are in competition with each other. So this is quite interesting, I would say. So anyway, clearly we need understandable tools and explainable results, and that's why also there's a lot of talk about trustworthy, explainable AI. That brings us to data science. And as every science, data science should be based on scientific methods. And I don't read it all. I mean, you will get the slides, and you can also look it up on the internet. But what it says over here, it involves careful observation, applying rigorous skepticism about what is observed. And that should be applied. And here's an example to warn you. This is about stock markets. And of course, there's a lot of data about financial markets out there. So one of the favorite application areas of data science. And back in 1997, a Nobel Memorial Prize in Economic Sciences was given to Merton and Scholes. And Scholes is known for the Black-Scholes model. which is basically a model to determine risk in the financial markets, and that allows you basically to calculate the risk and to handle risk reasonably well. And then the thing that politicians always expect from scientists happened. This theory was applied, and a long-term capital management fund was opened. A lot of billions went into this fund. It was applying that formula basically. It was a high leverage hedge fund. And then 1998, 1 year after the Nobel Prize, they needed a bailout. $3.6 billion had to be chipped in order to avoid that the world financial markets would collapse. And what was the reason? The reason is that actually this Black-Scholes formula assumes a bell curve, no distributed noise. Well, in fact, it turns out in financial markets you have a power law. That means extreme variations are more frequent than expected. All right, so data science then is not just about data analytics. It involves computer science, machine learning, math and statistics, empirical research, software development, and domain knowledge. And we'll come to this. So here's an intermediate summary. What data science handles better as compared to data analytics. And so data science considers confidence interval, makes sensitivity analysis, checks for correlations versus causality, checks for statistical significance, checks for overfitting, classification errors, biases, discrimination, and considers the role of noise. And now the next points that I'm going to discuss is the relevance of domain knowledge, the importance of qualitative variables, not just quantitative ones, and ethical issues. And as you know, in the beginning of the big data hype, there was one of the great success examples, which was Google through trends. And in fact, it seemed to work quite well to predict how many people would be affected based on search queries that people put into Google's search engine. And now it turns out this service has been switched off already for a long time, so 2015 actually, and it has been criticized by scientists quite a bit. And so the big data analytics approach apparently was not satisfactory. There are other approaches, though, that consider domain knowledge. And one of them is described in this science paper. Actually, there we don't even have big data, but we do is we combine two data sets and we consider some knowledge about the spreading process. So if you measure data about affected people around the world, you can imagine you have a globe, and whenever somebody gets a disease, it will flash a light. And those flashing lights should give you a better, and you should be able to find a model that describes that better. That's kind of the dream of understanding pandemic spread, right? And if you do that, then what you find is such a data set, widely scattered, not really meaningful. That means you understand nothing really. And the reason is that people take planes and spread diseases over large distances. And so what we did is we took travel data of passenger volumes to define a new kind of effective distance based on those travel volumes. I mean, two cities that had a lot of passenger exchange, like Frankfurt and New York City, were relatively close by, while some other cities that geographically may be close by, but didn't have much exchange of people, would have effectively a large distance. And if you do this, then you suddenly have a clear, diffusive pattern that allows you, A, to identify the likely origin of a disease, but also to predict what cities would be hit next by the flu wave or corona or whatever. And if you do this, you suddenly see linear relationships and meaningful correlations. And this kind of knowledge can be used to prepare medical staff and vaccination campaigns to be more effective. Unfortunately, I'm somewhat doubtful that this knowledge, even though almost everyone, I guess, has come across this paper, that this knowledge has been applied to fight the corona pandemic. So then the next point is relevance of qualitative data. So there's a lot of interest in global migration. And of course, there's been some debate also about this in Europe. Of course, politics had to struggle a bit how to organize it. And there's a lot of public debate, and that public debate is reflected in a data set called G-DELT. And you can look into how political decisions about asylum acceptance rates depend on who's reporting. It turns out it's not the number of articles written that matters, but it's the sentiment and how those articles report about migration. Finally, ethical issues. Now, if we apply data, we certainly don't want to do something wrong, in particular if it's about life and death. But in fact, there have been scientists working on applications of algorithms in hospitals, and this unfortunately has also to do with a very sad subject. You've probably come across this paper in Nature about what they call the moral machine experiment. So the question was, if not everyone can survive and some people have to die, who should be dying? I'm not sure the question in itself is moral, but not much later, in fact, this kind of thinking has been applied in the triage procedures around the world. All of that algorithm-based, in other words, data-based, your health data are being used and other data too, perhaps, to decide whether you would be allowed to live on or you would have to die. I think this is quite concerning. That's why we also wrote this article over here. And given all those tricky things with data science, it's even more concerning. But anyway, data science certainly has a lot to offer and a lot of value if done well, but also it has limitations. And in some cases, there are other approaches that are more powerful. So in some cases, they're highly accurate models like in physics. And in this case, we rather want to use a highly accurate model than an estimation of the behavior based on experimental data. You can understand it, you can do a stability analysis and scenario analysis, that has all advantages, but altogether, the best results, I think, are being obtained to combine data science with other scientific methods, experimental, model-based, simulation-based, and so on. But we need to be aware data science is a reductionist approach, and that may not always work. In particular for complex systems or complex dynamical systems. I like to show this graph. We're living in an age of big data, so we're coming from a time where we didn't have enough data to take good decisions. Now there's a lot of data. We can do evidence-based decision making, but data volume is exploding faster than processing power. That means the percentage of data that we can process is going down. And there's somehow dark data that will never be able to process that. Therefore, it needs scientists like you to decide what part of the data do we need to look at. So science is back in the equation. But the next thing is that as we network the world, the systemic complexity is increasing in a combinatorial way. That means it's even overtaking data volume. That means even though we have more data and better technology than ever, we're losing control over this world because of the complexity of those systems. So we often focus on objects or subjects, the nodes in a network, but the more we network people and things with each other, the more the links dominate over the properties of the nodes. So eventually, network properties prevail and the behavior of the system changes. And in those network systems, you often don't get the intended effect, but you get side effects, you get cascading effects or feedback effects. And that requires a different kind of control approach. I will touch upon this in my second talk. And I'd like to say in complex systems with heterogeneous elements, large degree of fluctuation and short-term predictability, we need a new approach. And many of the systems that we face with today in this globalized world are of this type. And I'd like to point out that machine learning can do a lot, but may face issues too. In particular, if you have certain kind of network characteristics and distributions, many social networks have kind of power law degree distribution. That is something which makes learning potentially difficult. Convergence may not happen. We have some noise also. Treating this infinity sign actually may turn out to be less easy than you may have thought. And even a famous example of complex systems, a cellular automaton called Conway's Game of Life, turns out to be hard to learn by machine learning, even though they're basically just 3-4 rules, simple rules describing that behavior. But kind of extracting it, distilling it from the dynamical data produced by the model is kind of getting back those rules turns out to be quite challenging. So in conclusion, what matters in data science, I believe, is ethics, good data, good methods, domain knowledge, statistical significance, and the consideration of properties of complex dynamical systems. Thank you very much.